Alright boys and girls, welcome back to Rock the JVM. My name is Daniel, and in this video I'm going to show you semigroups and monoids in functional programming and in Scala. So this video will assume that you are a comfortable Scala programmer because I'm going to use some pretty intricate Scala constructs. In particular, I'm going to use given instances and using clauses, and I'm also going to tell you what the equivalents are in Scala 2. And this video will also be helpful if you're interested in how the cats library works or how it's organized. I'm not going to use the cats specific semigroups or monoids. I'm going to derive them from scratch, and I'm also going to show you how the cats library is organized by how we're going to show our code. So as recommendations, as usual, I'm going to suggest that you code with me in this video, and whenever you need to refresh your memory, just refer back to this video or to its written form at the blog with the link in the description. So without further ado, let's see what this semigroup and monoid thing is about. So the goal of monoids, semigroups, monads, and other abstractions in functional programming is not so that we can inject even more math into an already pretty abstract branch of computer science, but because these abstractions can be very, very useful. So I hope the following examples will demonstrate many high-level constructs expressed as type classes can help make our APIs more general, more expressive, and more concise at the same time, which is almost impossible without the constructs that I'm going to show you. So this video will focus on semigroups and monoids, and you can use these techniques on other type classes as well. So a semigroup is very loosely defined as a set, in our case a type, plus a combination function. And this combination function will take two elements of that type and will produce a third value which correspond to that type as well. So long story short, a semigroup is a Scala trait. So I'm going to define that as a trait. I'm going to name this semigroup. And I'm going to make it generic in the type T. And this semigroup has a single method. I'm going to name this combine, which take two elements of type T. So an A and a B, both of type T. And this function will return a third value of type T. So this is basically it. This is a semigroup. Now, with this trait, we can create instances of semigroups which are applicable for some types that we want to support. So I'm going to implement a semigroup, for example, for integers, where the combined function between two integers will produce a third integer, and I'm going to use the summation function for that. So I'm going to define an int semigroup as a semigroup of int, and this will be a new semigroup of int where the combine method will take two elements a and b and will produce a third. I'm going to say a plus b. So this is an applicable semigroup of int. This is essentially a combination function between two integers producing a third. And I'm going to define an equivalent combination of strings. So I'm going to simply copy that, and I'm going to name this string semigroup as a semigroup of strings. And this will be a new semigroup of string where the combination function between the two strings, so I'm going to have an A which is a string and B which is a string as well. Now, in order to make these semigroup instances, which are essentially two arg combination functions, actually useful, we're going to follow the type class pattern. And we have a video here on the Rock the JVM channel about type classes and why they're useful and why this code organization actually works. And you can check that out. I'm also going to leave a link in the description. So we're going to follow this pattern. And we've already defined the general API of the type classes trait. So we're going to turn these type class instances and turn them into given instances. Of course, we have a video here on the Rock the JVM channel about given instances in Scala 3. It's so new that you're probably going to want to check that out as of the moment of this recording. And I'm going to define an object here. I'm going to make it an object. Let's call this semigroup instances. And here I'm going to move these two values. So I'm going to move them inside. And instead of placing them as separate vals, I'm going to have them implicit, either implicit vals in Scala 2 or given instances in Scala 3. So I'm going to have given in semigroup of type semigroup int, and here you can either use the equal sign, which is a given alias, or you can simply say with, which is the syntax of Scala 3 with the appropriate functionality of the semigroup which you want to make as given. And I'm going to have a given here as well. And instead of having equals this thing, I'm going to have with. Okay. Now, in order to be able to use these instances explicitly, we may need to summon them either with a summon method in Scala 3 or with implicitly in Scala 2 or with our own structure, which we are going to define here. I'm going to define an apply method. So I'm going to have an object semigroup, and I'm actually going to put that above, and I'm going to define an apply method, which takes a type argument t, and given its given the presence of an implicit semigroup of that particular type t, I'm also going to return that. So I'm going to have a using clause, so using instance, which is of type semigroup of t, and this will return a semigroup of t, and I'm going to return that particular instance. So basically this is an implicitly method or a summon method in Scala 3, but this is much prettier because we can summon a semigroup t by simply calling this particular constructor. And after this, we can use our semigroups to obtain new values. So we can, for example, have an import. So I'm going to say import semigroup instances.given, such that we can import the given instances in the main scope of this object here. So we can derive a val, let's call this natural in semigroup, as semigroup of int. And by calling the apply method, I'm making sure that I have a given instance in scope, and so I will return that particular instance which I can use to obtain new values. And of course, I can have a string semigroup, and I can copy that out. So I'm going to have string, and I'm going to name this natural string semigroup. Cool. And now with these two semigroups, we can obtain values of type int or string by calling the combine method. So I can say, for example, let's call this meaning of life as natural in semigroup dot combine. And combine will take two arguments of type int. So I'm going to have 2 and 40, for example. And this will return the meaning of life, 42. Or we can have, let's call this favored language as natural string semigroup dot combine. And I can pass two strings like ska and la. So I hope that by this point, nothing that we wrote so far is rocket science. So why do we need this fancy structure when we have the plus operator for ints and the plus operator for strings? Why do we need this whole structure to combine two integers or two strings? So let's assume you're creating a tool for other programmers, or in your big application, you are defining some very common data structures, and you want to expose the ability to collapse, for example, lists of integers into a single number, for example, their sum, and collapse lists of strings into a single string, for example, their concatenation, as given by these operations. So aside from instant strings, you want to support many other types, and perhaps others that your users might need in the future. So without semigroups, you would write something like this. You would need to define a method, let's call this reduce integers, and this will take a list as a list of int as an argument, and this would return an int, as list.reduce underscore plus underscore. So you would collapse this list of integers into their sum. And if you want to support strings, you would have a reduce strings, for example. And this would be a list of strings, and you would return a string, and you would have pretty much the same implementation, and so on for pretty much every other type. So look at this API. You basically have to repeat every single implementation for all the other types. So I hope this rings a bell because these look identical. So we want not to repeat ourselves. So in our quest to make things general and also extensible for the future, we can collapse our million different API methods into a single one. And we can write that in the following form. I'm going to have reduce things. So we're going to make this generic, meaning that it will receive a type argument t, and I'm going to pass a list of t, and I'm going to assume the presence of a semigroup as semigroup of t. Now, this will produce a type t, and I'm going to use this semigroup as the combination function of this reduce method. So I'm going to have list.reduce, and instead of using this plus operator, I'm going to use semigroup.combine. And in Scala 2, instead of this using clause, you would have an implicit parameter here, and you would be done. And anytime there is a given semigroup for the type you need, you simply call reduce things with that particular list, and you're done. So for example, if you have this import with semigroup instances.given, you can reduce things with a list of integers, let's say 1, 2, 3, and this is the number 6. Or I can have after that reduce things, and I can pass a different list for which I have a semigroup in scope. So I have a list of I, and then the string love, and then the string Scala. And this will be the string I love Scala. So this is not only more elegant and more compact, but this can be applied to any type you might ever need, provided you can write a semigroup instance for that type and make that a given or an implicit in Scala 2. So long story short, a semigroup helps in creating generalizable two-arg combinations under a single mechanism that you can then use in very, very general APIs. So this is one of the benefits, but still we can even move further and make our API even better looking and more expressive. Because we have semigroup as a type class, we might want to create an extension method that is applicable for any two items of type T for which there is a semigroup in scope. So in Scala 3, we have an extension method construct, which in Scala 2 might be implemented as an implicit class plus a method. So I'm going to have an object here, and I'm going to call this semigroup syntax just for a better organization, and I'm going to define an extension method. So I'm going to have an extension, and given a type T and an element A of type T, I'm going to define a method that I see as plus between these two bars, so this combine, shorthand combine method, and this takes another element of type T for which there is an implicit or a given semigroup in scope. So I'm going to have using semigroup as a semigroup of T. And this will return a value of type T, and the result of this method is going to be semigroup.combine with A and B. So given a semigroup, we can say A plus B, where this plus is between bars, so A combined B, by using that semigroup. So we can then say, let's call this meaning 2, because we have an implicit semigroup of int in scope, I can say 2 bar plus 40. And the bar plus method is applicable because I will import semigroup syntax dot underscore, which will also import the extension method. So this will import the extension method and will make this combine method applicable or unlocked given the presence of a semigroup of int in scope. And you can use this bar plus bar or combine method for strings as well, because you also have a given semigroup of strings in scope. Now, with the presence of this combine method as infix in scope, we can make our very general API even better looking. So I can define, let's call this reduce compact, which takes a type argument T, for which there is a semigroup in scope, and we write that shorthand with this colon. This is called context abstraction. So T colon semigroup means that the compiler needs to find a semigroup of T in scope. And the proper argument of this method is a list. So let's say a list of T, and this will return a T. So I don't need to specify this using semigroup of type T here as a second argument list, because this colon semigroup takes care of that. But in this case, I don't need to use the semigroup by name, but I'm using the presence of the semigroup to use the extension method. So I can say list.reduce, and instead of using that plus operator, I can use the combine operator underscore bar plus underscore. So the combine method here is used as an extension method given the presence of a given semigroup in the scope of this method. So notice how compact this API method now is in its implementation, and also in its looks, in its signature. So all we need to do is say reduce compact with a list of integers, and we should be done. So essentially we have one method to rule them all. So this is one of the reasons why we use semigroups, monoids, monads, traverse, foldable, and very, very many other type classes, so that we can generalize our APIs for any type for which there is an instance of our type class in scope. All right. So I hope the utility of semigroups now is apparent and more understandable for those of you who need it in your functional programming code. Now, with the background of semigroups, monoids should be a piece of cake now, because monoids are basically semigroups with a twist. Besides the toarg combine method, monoids also have an identity, also known as a zero or empty element. So the property of this zero element is that combining that zero element with any element will return that particular element. So let me define the trait. Let's call this monoid, which is a monoid with a generic type argument t and extends semigroup of t. So a monoid will have the same combine method, and besides that, we will also define, let's call this empty or zero, let's call this empty, or zero element, which is of type t. So the method empty will return an element of type t for which empty plus x is x for all x in the type t. All right, so this is the property that the monoid needs to uphold. Now, if you want to implement instances of this monoid for ints or strings, I'm going to define an object, let's call this monoid instances. And I'm going to define a given, let's call this int monoid, as a monoid int. And with, I'm going to define the combine method, which takes two arguments, a of type int and b of type int. And this will return a third value of type int, and this will be a plus b. And let's call this empty, which returns an int, and the zero value for this combination function is the number 0. And for a given, let's call this string monoid, as a monoid string with, and I'm going to define the combine method, which takes two elements. Let's call this a of type string and b of type string. This returns another string, and this is a plus b, in which the context of plus means that we're concatenating strings this time around. And with respect to concatenation, the empty, or the neutral value here, is the empty string, because concatenating any string with empty returns that particular string. So these properties will uphold for the int monoid and the string monoid. All right, now since monoid shares the two arg combination function with semigroups, there's no point in adding yet another extension method, which is still called combine, since semigroups are already sufficient for unlocking this method. So if you import the int monoid, for example, you also have access to the combination function on int, because this int monoid is also a semigroup. So this property is satisfied. Now, the only thing that we might want to change is the organization of these given instances, because we have two given instances for monoid and two given instances for semigroups, and the implementations for semigroups are now redundant because the monoids also are semigroups. So they might come in conflict if we import both semigroups and monoid, because their monoids are also semigroups. Therefore, it's usually a good idea to organize type class instances per supported type instead of per type class. So instead of having the int semigroup and string semigroup in an object and having the int monoid and string monoid in another object, we would rather combine those into an object that I'm going to call int instances. So I'm going to aggregate all the type class instances for int, and I'm going to define the monoid and move it here. And I'm going to define another object, string instances, and I'm going to move the string monoid below. So I'm going to move string monoid here in the string instances, and I'm going to do without the monoid instances and the semigroup instances, because all of them are now in the int instances and string instances respectively. And for the sake of my code compiling, I'm going to move these and put them at the top. And I'm also going to move the monoid definition underneath the semigroup definition. And now we have semigroup with its companion object. We have monoid, and then we have int instances and string instances. We might want to also define an object for monoid, which will also have an apply method. I'm going to cut that and paste it here, and instead of having a semigroup, I'm going to use monoid, and this will return a monoid t. And now in order to make our code compile, instead of importing semigroup instances.given, I'm going to import int instances.given, and I'm also going to import string instances.given. So I'm going to add another import, string instances.given. All right, and now our code compiles. Now, the way that we organize our code is very, very similar to how the cats library organizes most type classes. In fact, both monoids and semigroups are already implemented in the cats library, and you can use them by importing cats.semigroup, which will give you access to the type semigroup, and cats.monoid, which will give you access to the monoid type class. And the imports here are very, very similar. Instead of importing int instances.given, you would import cats instances int underscore or int.given in Scala 3. So this will be the int instances analogous import in the cats library. And the other APIs are identical to what cats offers. For example, the combine method is identical, and then the syntax organization is also very, very similar. I'm pretty sure that cats will be rewritten in Scala 3 with extension methods instead of implicit classes. And this import is very, very similar. If you want to use the cats library, you would import cats.syntax.semigroup.given in Scala 3. And notice how very similar these imports are in order to have access to this extension method, which, by the way, it has the exact same form. And we discuss a lot of other aspects related to semigroups and monoids and much more and many other type classes in the cats course, which is dedicated to the cats library, and you can find it at Rock the JVM with a link in the description of this video. So in this video, we discussed two common type classes used in cats and other functional programming libraries, and we showed what kind of practical problems they solve besides the mathematical abstractions. So hopefully after watching and coding alongside this video, you'll find that such type classes are really not that rocket science, and you'll start to use them more in your Scala code once you understand their utility. So in the description to this video, you'll find links to everything that we've discussed, including a link to the cats course. And if you like this video, go ahead and click the like button for me and subscribe to the channel for more videos like this. And follow me on Twitter and on LinkedIn and here on YouTube for more content like this, including updates on upcoming material. Now, I'm dying for feedback, so please leave your comments to this video. I read every single one. And check out the Rock the JVM website. I have tons of content and premium content on Scala and functional programming and cats and Akka and Apache Spark and so much more. Until next time, I'm Daniel, signing off.